And where we want to go, if you're lucky enough to have an access panel like on the Buicks here, we'll come back in here. And here's our access panel. And we have 5 bolts in there, 7mm socket will take care of fitting the heads of those bolts. So I'm going to be removing those 5 bolts. Now if you get the 5 bolts out, you're going to find there's going to be a sealant under here like a gasket. So I'm just going to take a screwdriver and try to work and break this seal. Okay. Now, let me get an air hose. I'm going to kind of blow off in there. So I'll be right back. All right, we'll get a little bit closer look in here. This whole assembly right here is for the fuel pump, level sending unit here. It's all built together. Over here we have the fuel pressure sensor. Over here we have this is for the sending unit. This is what we have interest. Over here, I believe this is our pressure line, fuel pump pressure line. This one is the return. And this is held down by a locking ring. You could probably take a brass punch and try to, turn this thing, and it goes counterclockwise to come off. I see there's a lot of rust and corrosion built on here, so hopefully it won't be too bad. But let's get to this here fuel level sending unit connector. Take this here connector. It's got this here tab to hold it in. Now let's see if I can just release this connector. And there we go. Okay. Alright, so now we'll get our diagram here. We'll come back and take a look at this thing a little closer. Alright guys, if you look real closely, you can see there's a letter A on this fuel level sending unit. It's going to be a purple wire. There's my purple wire right there behind my T-pin. The other end, the other wire for this here sending unit is on D, letter D. So let me flip it over. Hopefully you'll be able to see it. And you can see I have a T-pin on that. And you can see the color of the wire is a black with a white stripe. So that's the 2 wires for the fuel sending unit. Alright, so our first test, we're going to leave it open, disconnected, and let's just see if our fuel gauge is going to go all the way to pass full. Alright, let's turn the ignition on. Let's see what it does. Okay, you see it went all the way to full, maybe a little bit past it. Looks good. Okay. Alright, now those 2 wires, that purple and the black and the white, are going to jump together. Now, let's go to the ignition switch, turn it on, and it should go back to empty this time. Alright, let's put the switch in, key in rather. Let's see where it goes. Ooh. Right on empty. Okay? Alright guys, so now that told us 2 things. We know that the wires from the sending unit are good all the way up to the PCM. We also know that the class 2 network is working because the fuel gauge is working. Because the PCM has to transmit that data from the fuel sending unit, which gets to the PCM. So it's got to go from the PCM to the IPC. That's the instrument panel cluster, which then in turn is going to take care of our gauge. Alright guys, I want you to take a note of this. We have a mistake in the wiring diagram. If you look right here, you notice it says ignition, implying that you would have like 12.6 volts when the engine is off. Okay, so what I'm going to do is I'm making a check of that right now. So I have my voltmeter leads right out here across the sending unit with it unplugged, as you can see right now. Okay, see it's unplugged. I'm across the purple wire and the black and white wire. And if you look right here, you can see I have 5.01 volts. So what we have there is a 5 volt reference. Okay, and I was wondering about that because if this voltage varied right here, you know, from 12.6 to 14.2, then of course this voltage across this here sending unit is going to vary too, which is going to give you an inaccurate reading. So I was a little bit thinking about what's going on with this, so that's why I'm measuring it. So now we know that's a 5 volts up here at the top. 5 volt reference, not an ignition voltage as they show right here. Okay? Alright, now what I have right now is I have a 100 ohm resistor wired in series with the ammeter. I measured the resistance of this here resistor, and it's 98 ohms. And I'm looking right now, we're going to call this 14.6 milliamps. By knowing these two values here, we can actually calculate the resistance value inside the PCM. We promised in the previous video, I wanted to know what was the value of the resistance inside the PCM. Now with the previous measurements that we made of 5 volts that we found feeding this here circuit, and also we saw that the current going through here is 14.6 milliamps. Let's see if we can calculate that. Alright, we're going to start off. There's our resistance that's inside the PCM. Here is our fuel sending unit. And we already know that of course that resistance is 40 ohms to 250 ohms, and that equates to being empty, and also over here that will be for full. This is our ground connection. Our 5 volts is up here. We know that the PCM is looking at this here voltage, which is basically the voltage that's across the fuel sending unit, and of course that will vary. That voltage will vary depending on what the resistance is, and as I've mentioned, the lower the resistance, the lower the voltage. The higher the resistance, the higher the voltage. Okay, so the PCM looks here for that voltage. Okay, we know that the current that we measured down through this circuit, call that I, and we know that that was 14.6 milliamps. Now, there's also this current, when it's coming down, there's also going to be a small portion of current going out to here. Now this is typically what's going to happen when you have an analog voltage that this is looking at, the PCM. It cannot directly read an analog voltage. So that analog voltage has to get converted into a digital format. So right at this point, just so we're clear, this is an A to D converter. So it will take that voltage that's analog and it'll turn it into the ones and the zeros that the microprocessor needs to work on. Okay? But this current is going to be so small, it could be down into the nanoamps or maybe the microamps. So for this current, we can disregard it. Okay? Alright, so the current that's coming down we're going to look at is 14.6 milliamps. Alright, we know, we don't know this resistance, we'll just call them Rx. This one down here we can call them, say, R2. That would probably be like R1 and R2. But anyway, the X to say that's an unknown. Now if we go to Ohm's law, we know that voltage is equal to the current times the resistance. Okay? Alright, now looking at this, we know that if we look at this, say, for 98 ohms, right? Because remember, that's what we put in as our resistor. So let me go ahead and let's correct that. So we know that this is going to be 98 ohms. It was a 100 ohm resistor. Because of the tolerance being plus 5%, when I measured it, it was 98 ohms. Okay? So let's see what the voltage is across this resistance, which is 98 ohms. Alright, so our resistance is 98. Our current is 14.6 milliamps. We convert that into amps. So we move our decimal point 3 places to the left to convert it to amps. So now we have 0.0146. We multiply those two values together. Let me get a calculator. 0.0146 times 98 .0146 times 98. And I have 1.4308 volts. I'm going to call that 1.43 volts. That's how many volts that's across this resistor if we were to measure it with a voltmeter. Now, using Kirchhoff's voltage law, we know that voltage drops across resistors in series is going to equal to the supply volts. So to figure out what is the voltage across this here resistor, we can take and we'll say 5 volts minus our 1.43 volts, and we're going to get 3.57 volts. Okay, so across here we have 3.57 volts. Okay, and our 1.43 volts is across this one. Now, we want to know what is the value of this resistor. So going back up over to Ohm's law, now we want to know resistance. So we transpose the equation. We divide both sides by I. That still makes the equation equal on both sides. The I's will cancel out. Now we're left with R is equal to voltage divided by current. We take our voltage that's developed across this here resistor, which is 3.57, and we divide it by our current that's coming down through that resistor. Remember, the current anywhere in a series circuit is the same. So that's going to be 0.0146. So I divide that, 3.57 divided by 0.0146, and I got a value of 244.5. Now, I thought this was a little bit odd value since it's not a standard resistance, but I did a little research. It turns out that the value that's up here is 243. So I'm going to say that this is 244, what we calculated, but what we really came out with as far as what's up here is actually 243. So we came very, very close. So we do now know that that value for that resistance is 243 ohms. Now this resistor here is a precision resistor. I looked it up. It's usually it's a surface mount resistor. Has a tolerance of 0.05%. You could even get it down to 0.01%. I don't know what percentage tolerance they use, but either way, it's a pretty tight value resistor. So this is what we've got. 243, and we also have our 98 ohms. Now while we're here, let's do one more thing while we're in school. Now that we know that that value is 243 ohms, and we know, say, our sending unit is, say, for empty is 40 ohms. Let's try that. And we know we have our 5 volts here, and we know we have our ground connection here, and we know that the PCM is looking out here. Okay, volts out. Okay, so what if we wanted to know what is the voltage developed across, say, this here sending unit if it's in an empty condition, being at 40 ohms? Okay, so what we can do now is we can use the voltage divider rule. The voltage divider rule is, and let me just label this as R1, and we'll call this one R2, for resistance 1 and resistance 2. Okay, if I want to know what's the voltage out, which is across the sending unit, then I can say that V out is equal to this here resistance. This is the one that I want to know the voltage across, so I'll put him up here on the top. I divide him by the total resistance, which is R1 plus R2, times the voltage that's coming in. the voltage coming in is our 5 volts. So if I do my V out is equal to R2, which is 40, divided by R1 plus R2. If I look at this, I'll get 283. 283 times 5. And if I take and divide that out and multiply it, 40 divided by 283 times 5, you can see that I get pretty close to 0.71 volts. Alright, so 0.71 volts. This is equal to when you're at empty. Okay. Finally, if we want to do the other one, say V out is equal to R2 divided by R1 plus R2 times voltage in, and this time we want to look at it when it's full, right? So there's the one for 40, which is empty. Now let's look at the one for 250, which is when it's full, and we'll come down to this one. Then we'll say R2, which is 40, divided by 243 plus 250. That looks like that's going to be 493. So 493 ohms times 5, and I divide and multiply 40 divided by 493 is equal to that times 5 is equal to this 40. I'm sorry, 250. 250 divided by 493, and now that's where I'm screwing up right there. See, R2 should be 250, so it's my bad right there, guys. Alright, so 250 divided by 493 equals this times 5 equals this, and you can see that I have 2.53 volts. Okay. Okay. All right. So now we know that the min and the max voltage that should be on that fuel level sending unit should be say we're going to round it off approximately 2.5 volts to, sorry, that's the full. It's going to be 0.71 volts, right? This is when it's empty, and at full it's going to go to, we said 2.53 volts. Okay, this is the min and the max that the computer is expecting to see. So now it knows when to throw a code. Okay, and let's go back to the codes there, that high circuit code, and let's take a look at that. And also we'll take a look for the other code, which is a P0463, when it throws a code for the low voltage. All right, let's go back to our trouble code again. P0463 circuit high voltage. Now look right in here. This is what's going to set this code. It says the PCM detects a full level sensor voltage that is more than 3 volts for at least 10 seconds. Now we went over this in the previous video, but now I'm showing you how it knows that when it gets to this volts, it knows there's a problem. As we already saw, 2.53 volts, or say round it off to 2.5 volts, should be the max. So you only have a half a volt to spare there. So if it sees 3 volts, it knows there's a problem. Now let's take a look at the other one, which we figured and calculated to be 0.71 volts. Now this one is for the P0462 fuel level sensor circuit low voltage. Now we go down here and we can see that the PCM says detects a full level sensor voltage that is less than 0.4 volts for at least 10 seconds. So it's not a whole lot of leeway there, you know, far as in the span of voltage. Once it drops outside that range that we just looked at, and it stays there for 10 seconds on either one of those, then we know that the PCM knows there's a problem there. So just wanted to cover that for you guys so you can know how does a computer know when there's a problem. As it might be good to talk about this here sending unit. How does it work as far as, you know, we want to look at the actual sending unit, and we can apply that back to what we've already talked about on the Bach Board of Knowledge. Alright, let's take a look at this thing. The sending unit is normally in position on the side of the little canister, just like you see right now. This is the empty position. We go up, that's the full. Alright. Now let's look at this here little innards on this thing. Hopefully you get the light here right. Okay. See that okay? Mm-hmm. Alright. Do you remember that when we were in an empty position we had the 40 ohms? Well, there's that resistor right here. A little resistor right there. That's 40 ohms when you're in the empty position. Okay? This end of the wire will be connected to the ground connection. Okay? This other one right here is going to be going back up to the 5-volt supply. Alright? Do you see this here black? It's running all the way across here. Mm-hmm. It's running continuously from one end to the other. That is the resistor. That's that total fixed resistance that we talked about. Okay? From one end we have our fixed 40 ohm resistor, then we have our continuous carbon resistor here, and then we get over here we have 250 ohms. Now the wiper that we talked about is sliding across this here segmented track, as it's called, right here. Now each one of these segments is connected to a small portion of this here resistor. May be hard to see, but each one of these segments is connecting to a part of that resistor, that one up here on the top, and that gives us our resistance. Now let's take a look at this here wiper while we're at it, so you can see what's actually going on. If you look down in there, you can see it looks like two little springs, and in this one over here on this side you can see like two little tips out there sticking out. That's sliding on this here track on the bottom. That's called a solid conductor track. And if you notice, you remember on the diagram that the wiper was connected to one side of the other total fixed resistance. So you see, there it is, connected together through a strap. And if you look right down there on this little spring wiper here, there should be two little tips sticking out just like over here. Well, you can see that one of them is gone, the other one is kind of like bent up. So this is making an intermittent contact all the way pretty much across this here segmented track. So that's what's wrong with this. So there's no repair on this here. Okay, so you pretty much got to get a new sensor. I have in the past, you know, you sit there and you can push down on this, you know, trying to make a connection. Sometimes what will happen is these here bushings, they will get worn. If you look right here, see we got some play there, and you got to remember this thing is sitting up, so now it's actually sitting out. So that can give you some intermittent connections. My recommendation is just get another one. I have tried once in the past. I sit here and play with one of these things. I get it, looking good. It lasts about a week. Next thing you know, your gauge is going back to varying again, because you got to look at about the temperature. It's expanding, contracting, and this here spring is very delicate. If you want to be done with the job, replace it and you don't have to worry about it. But if you want to sit there and play with it and work on the springs and all that kind of stuff, I'm happy for you if you get it for work. Okay? So anyway, if you also look at this here sending unit, a lot of them have different profiles. Some of them called multi-slope profiles because of the configuration of the tank, the way it's molded and shaped, and going around, say, a drive axle. If you got say a rear wheel drive or your spare, tire compartment, then the tank might be molded. Okay, so they would have actually different profiles where these here segments, okay, because of those tank configurations, it's possible that this here sending unit may not be linear from one end to the other. Okay, so basically your fuel level will drop, and as it drops, this will drop, but as this drops, this may not be in proportion to the amount of volume of fuel that's left in the tank. Now looking at this one right here, this to me looks to be a linear sending unit. I'm saying that because I can see the segments on here and they seem to be all equally spaced out. If you look right here, you can look for yourself. If you get a close look, if you look at all of these here segments, they all appear to be, to me, equally spaced out. If we look over on this side, they all seem to be the same. But I'm going to hook this up to a scope, and I'm going to hook it up, and we're going to put the pull-up resistor in there just like what's in the car. I'm going to feed a 5-volt supply. I'm going to move this. Now I can get this to work if I take it and hold it up, make pressure with that wiper to that segmented contact, and then I'm just going to move it and do a sweep, and then we're going to look at the response curve, see what kind of slope. My guess is, looking at this segmented track, it looks like to me it's going to be linear. Alright guys, what I got here is I want to know the angle of sweep that's up here on this resistor card. Looks like 90 degrees, but let's don't guess. So what I'm going to do is I got my angle cube on here. I use this for when I'm doing some woodworking, so I don't make sure my saws are, true. I'll try to zero this thing. I mean, this thing is very sensitive. So just touching it, we'll get this thing off. Trying to zero it to get as accurate as we can. Yeah, 0.9. Okay.
Oh, there you go.
Alright, so I'm going to just go ahead from there. This is 0 degrees, and I'm going to just sweep this thing. Let's just see what it comes up to be. It looks like 92.3. I'm sorry, 82.1.
Where do you see that?
Right here. It's upside down. It's 82.3. Alright, that's what we'll call it. Maybe one more sweep. Okay, still 0.
82.1.
Alright, and then it went to 82. Yep, that's all the way up. 82.3. That's what we'll call it. Okay, 82.3 degrees. Okay. Alright, now what I'm doing now is I'm going to do a test to look at the linearity of this here fuel sending unit to see what kind of slope it is. I want to see how linear it is. Looking at the segments on there, it looked like to me like they were pretty evenly spaced, so I'm thinking it looks like it's linear. But we're going to do a little test here. Nothing like experimenting, right guys? Alright, so look, here's what I've done. We're going to hook it up just like what we saw when we found out on the car. We have our 5-volt DC, which I have that over here off the power supply. We also right here, we're going to feed that to the pull-up resistor, which is inside the PCM. We calculated that to be 243 ohms, and as mentioned earlier, this is an actual value that they do use. Alright, we're going to have our fuel sending unit, and then we're going to have that from 40 ohms to 250 ohms, where 40 is empty and 250 is full. I have my scope connected here at this point, which is the same voltage that the PCM will be looking at, and the scope common is hooked here. Now what I'm using for my 243 ohms is I'm using a decade resistance box, so I actually have then dialed in 243 ohms. You can see that with the switches. I have 200 here, I have 40 here, and I have 3 here. So 243 ohm resistor is there. Over here on this side is my sending unit. and you can see that we have it hooked up, and I've got my probe connections right here ready to look at it. Alright guys, we are looking at a sending unit. I have it hooked up. I am going from empty to full. I'm just trying to get a few traces here so we can analyze, looking at the profile of this here sending unit. I'm trying to make my sweep as consistent in speed. I didn't do too good there. There was a dropout. I'm holding pressure down on this wiper to try to get some good patterns here. So let's get a few of these here. Yeah, I didn't do good on that one. Let me get another bite on this thing. That one looked pretty good, the last one there, or the one before it. Okay, let's go ahead and stop the scope here. Yeah, these dropouts are where I took the pressure off of the wiper, so this here sending unit is definitely bad. These are dropouts where it's rising up and down, you know, because it's making intermittent contact. You remember from that spring I showed you, that's basically both of the tits there, you know, that was on that spring is pretty much gone. So let's back up here. Let's see what we can find something here. That one, yeah, maybe looks reasonably well. Okay, let's put a little bit of filter on this thing. Okay, let's go in so we can see what we got. So the higher your number here, the frequency, the less filtering as you go down. Basically just kind of get the hair off of it. That looks pretty good. Okay, so I think this is the one we were going to look at. Okay, first thing we want to do is let's just take a look at the voltage here. This is down here is where it's pretty much, that's pretty much where it was empty. If we look up here, we got 708 millivolts. Remember from our calculations we had 0.71 millivolts, pretty much right on the money. Let's look at it where it's full. Right there, looks like we've got 2.54 volts, and that looks pretty darn good too from our calculations. Okay, let's take a look at our rulers. Okay, so we have it set for degrees, which is what I want. I want to divide it up into 4 partitions, and that looks good too. We'll come back over here to the green dot to the right. We're going to drag him over here. We're going to start that. Yep, put him over just a little bit more. That's going to be 0 degrees. And then I'm going to drag another one out. And I'm looking at the one for the 720 degrees. That's what it defaulted to. So I'd say about right there. We can take a look up there. So this here is where it's plateaued out. So yep, that looks pretty good to me. Let's go back to our previous view. Now down here at 720 degrees, this is actually for defaulted to looking at 2 turns of a crank. But we can also change that. We can double click in there. Remember our sweep was 82.3 degrees. Alright, so now what we have is that this here line here is going to be for our empty. This is going to be for 1/4. This is a half a tank. This is 3/4, and this is full. Now where these lines cross is going to be representing theoretically where what our voltage should be at each one of these points for the for the increments of the tank, as I mentioned. Now if you remember, when we were at a half a tank, we calculated a value to be 145 ohms. Now with that value, that's going to turn out to be 1.87 volts. And so you already saw how I calculated the 40 ohms and the 250 ohms, so I'm just the same exact thing. So I'm going to type in 1.87, and you'll see the top line is going to drop down. So where it drops down is where that voltage theoretically should be for 1/2 a tank. But if you look here, one of the things you'll notice is that you'll see this is where our theoretical value is for that 1.87 volts where it crosses over. But you can also see that up here that it's a little bit higher to where it shows for where the actual value is, say for 1/2 a tank. So that implies, in looking at this, that if we took say a 145 ohm resistor, which is represented by this here horizontal line, then the gauge would probably actually measure a little less than a half a tank. So that means that we would have to add more resistance in there for it to actually put this thing to where it needs to be, as far as the pointer getting right on a half a tank. Now if we also take a look, you can see that from here, from a half a tank up to a full tank, you notice I mentioned there's a curve here. There's a slight curve, and this does not look symmetrical as far as from a half a tank all the way down to an empty. Now for this part of the curve, or the trace I should say, this looks pretty linear. The slope seems to be consistent, but as it goes from a half a tank all the way up to a full tank, then we can see that it is not consistently straight. So the slope is actually changing as we're going from a half to a full tank. Okay, so what we're going to do is I'm going to take my decade resistance box. We're going to go out to the car. All right, I'm going to dial it in for 40 ohms. We're going to see exactly where does the gauge go on the pointer. Where does the pointer go on the gauge? And we're going to monitor that. We're going to look at it. We're going to do the same thing for full 250 ohms. I'm going to put that in. We're going to see where does the pointer point at. And then we're going to come back and we're going to look at quarter, half, and 3/4, and we're going to just put in values to whatever it takes to get that pointer on the gauge to point to where it will be right on the mark on the gauge. Now just for giggles, while I'm there, I believe this gauge is marked in 1/8 increments. So I think what I'll do is I'll go ahead and I'll get those values while I'm at it, and then we can take all those values and we'll come back and we'll compare them to our theoretical calculated values when we were assuming that this here fuel sending unit had a linear profile. One other thing while we're here that we can look at, if you'll notice, you'll see that the voltage is kind of like it's stepping up. All right, this a lot of times they'll call this a step profile. What you'll see here is that the wiper is sliding across each individual segment. Now as it's sliding across each segment, then the voltage will rise because we just put a little bit of resistance in there. Then it's on that segment for this period of time, and now we just went up to the next segment, and now the voltage goes up because we put in a little more resistance, and we continue that pattern all the way up. Okay. Alright, so that's enough of the waveform. I think we've covered it pretty good. So the next thing we want to do is we want to go out to the car and we want to make some comparisons on these here resistances that I had just mentioned. Alright guys, right now I have a 40 ohm resistor in there. Let's just see where it comes up on empty. Looks to me like it is on the very last mark. Pretty close, dead on it. Okay, next one we're going to do is the 250 ohm. Alright guys, this is for the 250 ohm. That's showing full. Alright, go ahead and turn the switch on. Alright, this one should be for a half a tank. And we're looking at that, and it is actually a little bit less. It looks like it's on maybe 3/8 of a tank. Okay, so that kind of coincides with what we saw on the waveform. Alright, so guys, at this point what I'm going to do is I'm going to be switching in resistor values to get it to come, so this pointer on the gauge will go right to the mark. So no need for you guys to see all that. You're going to see what I'm doing, and then I'll get back with you in the next shot.
Okay, this is 170 ohms, half a tank, dead on. A quarter tank, 130 ohms. 1/8 of a tank, 107 ohms. 3/8 of a tank, 150 ohms. 5/8 tank, 187. 3/4 tank, 200 ohms.
Okay guys, now we got the values before, from the theoretical calculated values for, we were assuming, or I was assuming, that the fuel sending unit had a linear sweep over its entire path, but it looked like at the very top of the range from a half to a full tank, it looked like it varied a little bit. Now what I did is you've seen this table before, but what I've done is I have added in the 1/8 of a tank, 3/8 of a tank, and a 5/8 of a tank. And you've already seen all the other ones in here. So it's no need for me to sit here and go through every one of these. This here on the top is your resistance values. This is the calculated values that we assume was going to be okay. And then we went to the car, and then we got the values that would actually take to make this corner to go where it needed to go. For example, when I put in 40 ohms for empty, it went right to empty. At the same time, I took an actual voltage drop. Now you can look at this one here, 0.708. You can see it came right on the money. Okay, and then I went to the full, and you can see that it came out pretty close to being right on the money. And even down to here to the 3/4 tank, here was our calculated value of 197.5, 2.24, and it actually took a 200 ohm resistor to get it to go actually to the 3/4 mark. And here's the voltage drop for that. But as you can see, things start to get off a little bit. You can see the difference in the values here in the resistance and also in the voltages. And then by the time we got to a 1/2 a tank, what we thought was going to be 145 ohms with a 1.87 volt drop, it turned out it took 170 ohms to make it actually go to the 1/2 mark. Okay. Now what's interesting here is that on the slope of the fuel sending unit, when we looked at the graph from a 1/2 a tank all the way down to the empty here, it looked pretty much linear. So you would assume, okay, that from here, you would think the voltages and would pretty much coincide to match up. Okay, but you see that is not happening. Now that means there's one thing that's going on. When you get a situation like this and you know that the line is linear, then what's happening is the PCM receives that value, what that voltage is, and it is actually manipulating that value to correspond to the actual volume of fuel that's in the tank. So that's what we've learned from right here. So for you guys out there, if you have a car, 2000 Buick LeSabre, maybe in that range, and I can't swear to it about a Pontiac and Olds, and but if you wanted to take and if you wanted to say, what we found out is that if you open up your sending unit, it looks like it goes to full, goes a little bit past it, all right, goes a little bit past it. If you open it, now that is, so that's a valid test. If you short it, it'll go a little bit under empty. And if you actually want to put a couple of resistors there, say for a 250 ohm, you actually will get this thing to go to full. And for 40 ohms, it should go right to empty. But I guess anywhere in between here, depending on your car, it may not work, So, I mean, you could put a resistor value in there, and if you see the needle gauge move to go to some place other than, say, empty or full, you could say, well, the gauge is working, but is it right where it should be? You really can't say. But anyway, this will give you guys some values here that you can see the difference between the theoretical values and the calculated values, and some came in being pretty close, and a lot of them actually were off. Okay guys, that's going to wrap this video up. I know it's a long one, but I think it's a lot of information here, that's going to help you out. At least you understand, about sending units now and profiles on them, and calculated values, what's in the real world. And so the next video should be a little bit shorter. We're going to go in there, we're going to take this thing, remove it, and put it in. As you already know, we got a bad sending unit here. So the next video we're going to show how to do that. So we're going to take it out, put it in, and then that'll wrap this video series up. So stay tuned, we've got one more video to go. So you guys take care.